Hi, everyone. Thanks for joining in with us today. Welcome to Megger's first Testing Tactics webinar series with On24. Here you'll find you can move around the presentation space to your liking, as well as discover a few features, such as learning more about your presenter right over there, and being able to contact us for any offline discussions you would like over here. Jumping into today's topic, transformer winding resistance measurement field challenges. My name is Michael Fleischer, and I'm the digital marketing analyst for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you will see the Ask a Question window, which I will highlight here now for you. You can submit questions at any time during the presentation, and I will read questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Dinesh Chajer, Director of Technical Support Group. To assist with the question and answer session, we also have joining us Dr. Charles Nybeck, Regional Sales Manager, and Damian Robinson, Deputy Director of Application Segment Teams. With that, I will hand things over to our presenter. Thanks for joining in today, Dinesh.
Thanks, Michael. Good morning, everyone. My name is Dinesh Chajer. I'm the Director of the Technical Support Group, and I will be your presenter today as well. The topic for today's webinar is transformer winding resistance measurement and field challenges. And in this topic, we're going to talk in depth about winding resistance. It is one of the most common tests that field guys do on power transformers, both during the acceptance testing as well as the maintenance testing. When you talk about winding resistance, on the surface, it seems like a very simple test, basically Ohm's law. But there are a lot of technical complexities that are associated with this test. And the intent of this webinar is to cover those kind of technical details. We will talk about things such as what is the right test current that you should use for performing the test. What kind of role does the compliance test voltage plays in getting your readings stabilized faster? We will also talk about things such as the transformer winding configuration, what challenges it poses, the test instrument that you are using, what different test modes you can use. Some of the instruments can do the test in per phase mode. Others can do test like 2 windings at the same time. Then there are instruments available that can test all the 3 phases simultaneously. We will also cover safety-related aspect when performing this test. This test obviously applies DC current to a coil or a winding, which is inductive in nature, and energy gets stored in the inductor, which can be dangerous if you don't dissipate that energy. So we'll talk about the safety aspect of it, and we will go over some of the field results that would give you an idea of what best practices you can implement so that you get reliable and accurate measurement. We will also look at how to analyze your readings once you get your results, what are the pass-fail limits, and we will wrap up the session by talking about the last step, which is demagnetizing the transformer. We don't want any kind of residual magnetism in the core of the transformer because that can impact your other electrical test. And also when you put your transformer back in service, you don't want to run into any kind of inrush current or any other issues. So there are a lot of technical details that we're going to cover in this webinar. So stay tuned and let's get started. What I will do so that the streaming is good, I will turn off my camera so that way you can focus on the presentation. And at the end, we would certainly go over some of the questions that you would submit through the Q&A box. So let's get started. When we talk about winding resistance, the first thing is that it's a DC test. You apply DC current into the winding, measure the voltage drop, and then measure the resistance. The diagram that you're seeing on your slide is the diagram for the transformer equivalent circuit, and the two electrical quantities that are of interest is the resistance of the primary winding, which is this one, and the resistance of the secondary winding. If you have a three-phase transformer, there would be total 6 measurements, 3 on high side and 3 on the low side. The reason why this electrical equivalent circuit of a transformer is important is that when you're performing this test, you are not only just dealing with the resistance, but you're also dealing with the inductive component of the winding, which is represented by X1 and X2. So we will talk in depth about what role does it play when you perform the test. The other important thing that we need to discuss is the excitation circuit of the transformer, because we want to make sure that our current levels is enough, so that way we can perform this test accurately and reliably. So we'll talk about all these parameters as we go further into the presentation. So why do I want to perform this test? As I mentioned, that this test is recommended to be performed during the acceptance testing, commissioning, and also during scheduled maintenance. This is a very sensitive test. And the reason why I say that is that any deviation more than 2% is a cause of concern. So because it's a very sensitive test, you can pick up problems like if there is any shorted turns, any kind of open winding, if you have a loose connection, or if we talk about OLTC, which is on-load tap changer, if there is any tap which has carbon deposit on it, which would lead to the high contact resistance, you can pick up those kind of problems. When we talk about winding, there is an insulation aspect as well. So you can also identify things such as broken strands, defects in the insulation, which is over each turn of the winding. And then in the factory, it is used to measure the losses, which is I square R losses. And from there, we calculate the efficiency of the transformer. It is also used to perform, to measure the temperature of the winding. So that way you can find out what the temperature of the winding is by performing a heat run test. And all the last two ones, this one and this one, are basically kind of factory tests that they do to measure some of the parameters. Not only it is done during commissioning, but if there is any kind of troubleshooting that you need to do, or there is a transformer inspection, this is one of the recommended tests to check for any kind of winding issues. And as I mentioned, that in the factory, transformer manufacturer use it for the efficiency calculation and also to measure the winding temperature through the heat run test. Once the transformer is installed and in operation, from time to time, a transformer is taken offline for scheduled maintenance testing, and winding resistance is one of the tests that is being performed. There are times when there is a unscheduled outage where they are doing some troubleshooting, and again, winding resistance is a common test that is performed. So now let's get into the concepts or the principle of measurement. What happens when you run this test? So as I mentioned that when you perform this test, you are basically injecting a DC current into the winding, and what the goal is that you want to measure the voltage drop that is going to take place across the winding. And once you know the current, once you know the voltage, you can calculate the resistance of the winding. But there is more than that. Whenever we talk about a winding, you are talking about a series combination of resistance and inductance. And when we talk about that, it is a series RL circuit, and you are applying a DC current to it. And when that happens, what would happen is that there are two voltages that you would run into. One is the voltage drop across the resistance, which is defined by IR component. And then whenever you inject a current through a inductive circuit, there is going to be and because we are starting from 0 amps and going to a target current of, let's say, 10 amps. So because the current is changing, there is going to be a magnetic field that would get generated. And from that, there would be a voltage that would develop across the inductor portion. And that is represented by this component, which we define as L di by dt, where di by dt is the rate of change of current. As long as the current is changing, you will have that L di over dt component in the circuit or in the equation. Our goal is to stabilize the current. Once I stabilize the current, there is no more rate of change of current. And when that happens, you get rid of this L di by dt component, and then you can do basic Ohm's law to calculate your resistance. So in essence, the important thing is that when I start the test, I want to stabilize the current. That's the whole game. But as I mentioned, that when you inject a DC current to an inductive circuit, inductor does not like change of current. So it will provide a opposition to that flow of current. And we have to neutralize that effect of inductance. So again, I'm going to highlight this one more time. So the goal of this test is to stabilize the current to the target level as soon as possible. If your current is fluctuating and it's not stabilized, you will not get stable measurement. So again, that's our goal. We want to get to the target current and be there at a stable value as soon as possible. The other thing I want to highlight is that it's a 4-wire measurement. What do I mean by that? I don't want to measure the voltage drop across the leads. So what you do is that you apply the current through one set of lead set, and then you measure the voltage through another set of lead set. So it's a 4-wire measurement, and the leads that we offer, it is a Kelvin clamp, and it has the ability to have the current and the voltage connection with the same clamp. So that makes it easy when you perform the test out in the field. Again, it's a 4-wire measurement, so that way we don't record the voltage drop across the connection point, across the leads that we are using to perform the test. So going further into the principle of measurement, as I mentioned, what is the goal? The goal is to stabilize the current. And I want the change in current, which is this component right here, di by dt, I want that component to do what? Rate of change of current should be 0, meaning that I need my current to be stable. In order for you to stabilize the current, two things need to happen. One is that I need to have enough amount of current that I can inject so that I can establish flux and saturate the core. And the second is that the flux that's going to get generated, it should be enough for you to have a saturation of the core. And once there is a saturation of the core, we neutralize the effect of inductance. And once there is no opposition, it is much easier for us to get to the target level. So again, you want to be able to do two things. You want to be able to saturate the core with enough flux, and the definition or the equation for flux is the applied voltage times the duration for which you are applying the voltage. So it's volt seconds. That's the equation we're going to focus on. And you want to apply enough current so that way you can have enough flux and then get to the saturation level. The other thing that you need to be aware of is that transformer configuration and design plays a big role in how long it would take for it to provide you the stable reading. The time it takes for you to get the stable reading is directly dependent upon the time constant, which is represented by L over R. If you have a single phase auto, let's say 500 kV, 800 MVA single phase auto transformer, the L or the inductive portion is very high in that. And because those transformers are very efficient, there is a very small amount of copper losses or I squared R losses. So R is small and L is very high. So in effect, your L by R ratio is very high. And whenever you run into a high L by R ratio, which is the time constant, those kind of transformers will take longer time for current to stabilize, for core to saturate, and for you to get good stable readings. So again, the transformer configuration design also plays a big role when you're doing this test. We talked about these things just now. Inductor resists the changes in the current that flows through it. And because it opposes that change in current, Lenz's law comes into picture and it induces a voltage which is represented by L di by dt. And the time it would take for the current to get to the steady state level is purely dependent upon the time constant of the circuit, which is defined over L over R. Large inductive winding, as I gave the example of the single phase auto transformer, so large inductive winding with small resistance are the most difficult ones to test. And we have some examples that we would share from the field testing that would give you an idea of, depending upon the configuration of the transformer, what vector configuration it has, that would also be a critical factor when you perform this test. So in the previous slide, I mentioned that the game is all about getting a stable level of current. And for that, you need two things. One is the open circuit voltage, or we call it as the compliance test voltage. You need to have enough voltage for enough amount of time, so that way you have enough flux that can saturate the core. Remember the equation I said, flux is equal to volts times seconds. So again, higher the compliance test voltage I have, then shorter the duration for which I have to apply the voltage to generate enough flux. So again, higher the compliance voltage, better it is for you to have enough flux to saturate the core. The second thing that you need is the DC current. And you need to have enough current so that way you can get a stable current level. If you're going to use, let's say, 0.5% or 0.1% of the rated current of the winding, you will always struggle to get a stable current level because that current is not enough. And we have a couple of slides where we talk about what is the recommended current levels. So let's go into those two parameters, the open circuit voltage and the applied DC current. So we talked about this thing just now. More voltage you would have, less duration of time you would have to apply that voltage to generate enough flux. So again, higher the compliance voltage, better it is. A lot of time we get asked question, is 10 amp of test current enough? And I always say this thing that you just don't look only at the test current. You should also look at the compliance test voltage, because that's what would help you to generate enough flux in the circuit. So this is one very good example which would tell you the value of the compliance test voltage. So I have a transformer that's a 69 kV to a 13 kV transformer, a delta Y configuration, and you can see that the primary winding rated current is 200 amps, and the secondary rated current is about 1100 amps. It's a delta Y transformer. So what we did was we ran the test at 10 amps at 2 different times. In the first case, we had a compliance test voltage from one instrument at 67 volts. And you notice that I got my 3 measurement, and it took me about close to 30 seconds to get the measurement. But when I use a lower compliance voltage, let's say about 40 volt, you notice that my time to get a stable measurement was almost twice of what it was when I used higher compliance test voltage. One thing I want to highlight is that you would still get the same numbers. It's not that your numbers are going to change. I still see the same numbers, same readings. It's just that if you have higher compliance voltage, it would help you get to the stable readings much faster. So keep that in mind. Now let's talk about how much DC current you need to perform the test. The goal is that you should apply at least 1% of the rated current. So if I have a rated current of 1000 amps for my winding, I want to apply at least 10 amps. The other thing that IEEE standard talks about is that you don't want to inject more than 15% of the rated current. And there are 2 reasons for that. One is that if you're going to inject, let's say for that same 1000 amp circuit, if you're going to inject 150 amps of DC current, you might severely magnetize the core of the transformer, which we don't want. And then the second thing is that the current level of 15% may be high enough to cause heating, which would change the resistance of the winding. And you don't want your testing to change the resistance. And as I mentioned earlier, that winding resistance is a temperature dependent test. So more current, more heat, change in resistance. I don't want that. So again, you don't want to exceed more than 15%. A sweet spot is anywhere between 1 to 10%. That's the sweet spot where I would like to be when it comes to the amount of current I want to apply to run the test. One thing to keep in mind, if your test current is too low, what would happen is that you would get fluctuating reading for a long period of time. And that's a number one reason why people record measurements that are not accurate. So again, it is very important to make sure that you have enough current to get stable readings. And again, minimum that you want is about 1% of the rated current. I talked about this thing, using higher than normal test current can cause transformer core saturation with a lot of residual flux. And then also, if you have higher current, it can change the temperature of the winding. That could change the resistance that you're measuring. So this is another example where we did the test at 3 different levels of the current on the secondary side, and you notice that the rated current was about 900 amps. So the 10% off that is about 90 amps. So as long as I'm below 10%, I'm okay. So we did the test at 10 amp, 25 amps, and 50 amps. And you would notice that my readings are more or less the same. But the difference that you see is that if you use higher current, you would get your readings faster. So that's the advantage of using higher current. but you want to stay within the 10% limit, okay? Now let's go further into the concepts and understand what is happening when you run the test. So what happens is that when you start the test, your current is at 0 amps, and you want to get to the target current. And what happens is that the current would slowly ramp up, and it would try to stabilize. During this time, what is happening is that your resistance is fluctuating all over the place. And I certainly don't want to measure my resistance anywhere here. I want to measure the resistance when it's stable. And then during this time, what is happening, if you remember the equation, it was voltage is equal to IR plus L di by dt. As I'm generating more flux, the L di by dt component is reducing. It is constantly reducing. That's why my voltage is going down. And there would come a point of time when the L di by dt, when my current is stable, the L di by dt would go away, and then I have a constant voltage and a constant current would give me what? The constant reading, which is the resistance. That's what I'm looking for. So again, this would give you a good idea of what happens when you run the test. On the right-hand side, you have one more picture which shows you where you want to operate. The x-axis is your current, and your y-axis is your flux. This is what we call as hysteresis curve. And you want to have enough current so that way you can saturate the core of the transformer. I don't want to be operating here because here the current is not enough for me to saturate the core. So again, keep in mind that you want to have enough current so that you can saturate the core. Once you saturate the core, then obviously you take out the L di by dt out and you get good measurements. Now let's talk about some of the standards that recommend performing this test. The first one is the IEEE C571290, which is the standard for test code for liquid immersed distribution power and regulating transformers. And then we also have a field testing guide, which is C57.152, which is the field testing guide for oil-filled or fluid-filled power transformers. So both the standards recommend performing this test. Now let's look into how or what is the criteria for pass and fail of this test. So you have two ways to do the analysis once you get the readings. The first one is that you run the test on A, B, and C phase, and between the phases, the difference should not be more than 2%. The worst case scenario should not be more than 2%. Either it could be between A to B, B to C, or A to C. The difference should not be more than 2%. That's one way of analyzing the readings. The nice thing about that is that because you perform those three measurements about the same time, so you don't have to worry about temperature correcting the readings. The second way of analyzing the results is to compare the A phase readings with the A phase measurement that you took either during commissioning or during the factory testing. And the criteria is that you don't want to deviate more than 5% from the baseline measurement. One very, very important thing to highlight here is that you want to correct the readings to a common temperature level. Lot of time the nameplate would say 55 degrees C rise or 65 degrees C rise. What it means is 55 degrees C rise above ambient. And ambient we consider as 20 degrees C. So if the nameplate says 55 degrees C rise, you want to correct your readings to 75 degrees C, 55 plus 20, 75. And if the nameplate says 65 degrees C rise, you want to correct your readings to 85 degrees C. And then you want to do the same thing for your factory measurement or your commissioning measurement so that you're comparing apples to apples. The other standard, which is the NETA acceptance testing standard and maintenance testing standard, recommend performing this test on both dry type and liquid filled transformers. And it says that the temperature corrected readings should not deviate more than 1% between the phases and 2% for the liquid filled transformers. They also recommend performing this test on all the taps of the transformer. It's considered as best practice to do that. Again, this is the formula that you would use to correct the readings to 75 degrees C or 85 degrees C. Lot of time, majority of the instruments that are available out in the field, they have the capability of auto-correcting the temperature auto-correcting to whatever reference temperature you define, and you don't have to do all these calculation. But if in case you need to do the calculation, this is the formula that you would use to correct to either 75 degrees C or 85 degrees C. This is again one of the field example. You can see that I have the readings for the 5 taps of the LTC, and all the readings are already temperature corrected, and the software does it for you, where all the readings that you're seeing here, and here, all these readings are temperature corrected. So user doesn't have to do the calculations manually. The other very important thing to highlight is that you want to keep an eye on the winding difference between the phases. You notice that all the results are less than 0.5% difference, which is good because my criteria is 2%. I don't want to see a deviation of more than 2% between the phases. So that's what you should be looking at. Now, let's talk about the safety aspect of it, because when you are talking about a series RL circuit and you're applying a DC source to it, you are basically building up the energy in the inductor. And that energy need to be dissipated before you take your leads off. So let's say I connected my leads, ran the test, and now the current is back to 0. But the energy that was developed in that inductor is still there, L di by dt. So what I want to do is that before I disconnect my leads, I want to dissipate the energy that is there in the inductor. Because if I don't do that and I try to take the leads off, all of that energy would dissipate in the form of arcing at the point of disconnection. So I don't want to see that, because that could damage the test object that you're testing. It could lead to the damage to the test instrument. And even worse, it can cause, not so good thing for the person who is handling those leads or operating, making the connections. So again, it is highly, highly, highly recommended to make sure that you dissipate the energy before you take the leads off. And majority of the circuit instruments have an indicator on it which say discharge circuit. And there is a light that needs to go off before you can take the leads off. Once that light goes off, meaning that the energy has been dissipated through the limiting resistors to the ground, and now it's safe to disconnect the leads. So as I said, you need to be very careful about this thing, that lethal induced voltage can cause problem to the transformer under test, can cause damage to the instrument that you're using, and it can also cause personal injury as well. Again, this is the warning that you would see in a lot of users' manual, which says that an extremely high voltage can develop across the point where the connection is broken. So we want to make sure that the energy is dissipated before you take the leads off. So how do you dissipate the energy? Once you're done with the test should bring the current down to 0, and then it should discharge the energy to the ground circuit using the limiting resistors, and the discharge indicator should go off, and that tells you that now it's safe to disconnect the leads. We just covered these points. Now let's get into some really interesting test results from the field, which would help you implement some of the best practices, so that way when you go out in the field, you know that I'm doing the test properly and I'm getting my readings accurately and the most reliable readings that I can get. So this is directly from the standard, and this is very, very, very important. And I'm going to highlight this statement. It says that the polarity of the core magnetization should be kept constant during the resistance measurement. So if you have magnetized the core or the legs of the core in one direction, and as you move from A phase to B phase, you want to maintain the same direction in which the flux was set up in the previous test. And you will see that when I would explain some next slides. But again, you don't want to do effort twice, where you first magnetize the core in one direction, and in the second test, you're trying to magnetize the core in a completely opposite direction. That would take longer time, inaccurate measurement, and also your readings won't be reliable. So a reversal in magnetization of the core can change the time constant and result in erroneous reading. So again, I'm going to highlight, you want to maintain the direction of the flux that you're trying to set up in the core. You want to maintain the direction the same, and you will see that in the next slide. So you notice that I have 3 windings right here, A, B, and C, and I have 3 legs of the core right here. So if I were to inject the current from H1 to H0, you would use the right-hand rule and can easily determine that the direction of the flux would be in the upward direction for the first leg, or the A phase leg of the core. That flux, which is upward in direction, and that's why I showed it right here, that if the current is down from H1 to H0, the flux direction would be in the upward direction. Once you have set up the flux in the upward direction for A phase, you would notice that the flux is going in downward direction for B phase and downward direction for C phase leg. Because I'm doing per phase leg, I still have flux going in the B phase and C phase. So the direction of flux is, for A phase leg, it's up, for B phase, it's down, and C phase, it's down. So now I ran the test on A phase, got my measurement, the core is saturated and everything. What is the next step? I want to go to B phase and do the measurement. If I go to B phase and I try to set up the flux in the upward direction, I would be working twice hard, because the flux in the B phase is already set in the downward direction. So make sure that when you test the B phase, you maintain the direction of the flux in the downward direction. And I will show you in the next slide. So when you test the B phase, this time you want to inject the current from 0 to 2. I'm going to highlight that again. You want your current to go in the upward direction, so that flux is still in the downward direction, which was the original setup when you tested the A phase. And when the flux is going in the downward direction, now you notice that for A phase, it's going up, and for C phase, it's going up. So when I'm going to test the C phase, which direction do I want my flux to be in? In the up direction. So you notice that in the next slide, I want my current to be in the downward direction, so that flux can remain in the upward direction. So after doing all this thing, what really matters is that the connections that I'm showing right here, A phase, B phase, and C phase. So for A phase, for a Y winding configuration, I'm going to do 1 to 0. For B phase, I'm going to do 0 to 2. I'm going to highlight that again. Don't go H1 to H0, H2 to H0, and H3 to H0. No, you want to do 1 to 0, 0 to 2, and then 3 to 0. Okay? If you have a delta configuration, I'm not going to go into the same kind of description, but you would notice that the connection would be the same. Down for A phase, down for C phase, but up for B phase. So H1, H3, H1, H2, and H3, H2. So that way I maintain the direction of the flux. So that way I'm not working twice hard, I'm working in much smarter way. Again, this is for Y winding, 1 to 0, 0 to 2, 3 to 0. For delta winding, it would be 1 to 3, 1 to 2, this is important, 1 to 2, and then 3 to 2. Now let's talk about different transformer winding configuration. You can run into a delta or you can run into Y. Yes, there are some zigzag configuration, but primarily you run into a delta or a Y. When you test a Y winding, and I'm going to go one slide back if that's okay. Let's say I want to test Y winding and I'm going to do one phase at a time. The testing is very simple. You connect one lead to H1, one lead to H2, H0. So in that case, there is no current flowing in the B phase winding or C phase winding. So you are measuring A phase and the current is only flowing in A phase. But when you test a delta winding and you want to test A phase, there is one more path for the current, which is what? Going from B to C phase right here. You see that there is one more path for the current. So now, when I'm testing a delta winding, I have to neutralize the inductance of not just one winding. I have to neutralize the inductance of three windings, A phase, B phase, and C phase. And that's why it takes longer time for you to get stable measurement for a delta winding. It is very common that you would see that you run the test, it seems like that the readings have stabilized because only the A phase inductance has been neutralized. So a lot of people make a mistake to save the reading when it looks stable. But what really is going to happen is that after it has kind of stabilized, it would start fluctuating again because it is still waiting for B and C phase to neutralize. And then you have to wait some extra time, and then it would again stabilize. That's the time that you want to record your measurement. So again, when you're testing delta winding, you are not dealing with just one winding, you are dealing with all three windings at the same time. And if you look at this circuit, you have the A phase and the B phase and C phase are in series with each other, and they both are parallel to A phase. So keep that in mind that when you're performing this test, we call it that you are measuring the resistance between two terminals. We don't say that you are measuring the A phase because it's actually not just A phase measurement. It's a parallel circuit of A phase parallel to B plus C. So your effective resistance is going to be a combination of all those three circuits. So when you're comparing your results, make sure that you're comparing the results that were done in the same way. In the factory also, they should have done the test between the two terminals, for example, H1 and H3, which tells me that they have the B and C in series, which is in parallel to the A phase. If someone says that I want to know the resistance of A phase only, then you can do some simple calculation, and the assumption that we make is that B phase, C phase, and A phase have more or less the same similar readings. So you notice that B and C phase are in series. That makes it 2R, and the 2R is in parallel with A phase. That makes it 2/3 R. And if you want to know just the resistance of the A phase, basically whatever reading you get, you multiply that by 1.5, and that would be the reading of your A phase. Again, assumption has been made that A, B, and C phase, all three are similar readings. So now let's talk about out in the field what happens. When you perform this test, one of the important thing is that if you're doing the test per phase, meaning that I'm going to test A phase, then I'm going to test B phase, then I'm going to test C phase, there is a lot of manual work if you have to go up on the transformer, move the leads from A phase to B phase to C phase, and then do the same thing for the secondary side. So one of the advantage that's available is that the test set has 8 leads coming out. You make your connection one time, and then test set internally changes the source. Once you have tested A phase, the source would get connected to B phase. Leads are already connected, and then you run the test on B phase and C phase. And likewise, you do the same thing for the secondary side. So what it does is that it does the testing sequentially, but it helps in avoiding going back up on the top of the transformer to change the leads. You make your connection one single time, and then you run each of those tests sequentially. There is one other method that you can use, which we call as dual injection, where I'm injecting the same current in 2 windings. Let's say A phase of high side and A phase of low side. So notice how the current is flowing. I start the current, it goes into H1 winding, flows through the H1, H2 winding, and then I connected a jumper between H2 and X1. Remember the important thing, I'm connecting the 2 opposite polarity terminal. H2 is non-polarity and X1 is polarity. When I do that, the flow of the current in both the winding is in the same direction because I want to set up the flux in the same direction. Now, instead of having one winding trying to set up the flux, I have 2 windings helping me out to set up the flux to saturate the core and get a stable measurement. Not only that, I have 2 voltmeters available. One is V1, and then I have one more voltmeter available, which is V2. So now with the same current, I can measure the resistance of high side, and I can measure the resistance of the low side at the same time. So now instead of doing 6 tests, I only have to do 3 tests. And in each test, I'm going to get the reading of the high side and low side, A phase. Then I do the same thing for B and C phase. Here are some of the test results here. You notice that the first one is single injection where I ran the H1, H2 first by itself, then X1, X2 by itself. And it took me 60 seconds for the first measurement and 101 seconds for the second measurement. But if I were to do the dual injection, I was able to get the same readings in about 72 seconds. So it does save you a lot of time. And this was a small transformer. If you were to test, like big power transformers, dual injection is a very good method because then you get 2 readings in very quick amount of time. So there are 2 advantages. One is you're using more current to set up the flux. And second is that with 2 voltmeters, you can measure 2 resistances at the same time. These are some of the connections. I'm not going to go much into the connections, But the important thing to keep in mind is that you connect non-polarity terminal to the polarity terminal. So that way the flow of the current is in the same direction right here. Okay? These are just some examples. All of you would get the slides or the presentation, so that way you would know how to make the connections and everything. The one thing I want to highlight is that there are times where people test two measurement on the same side of the transformer. So for example, let's say I have a Y delta transformer. So the Y side right here has three windings, A, B, and C. And you notice the current is flowing from H1 to H0, then to H3, and then coming back to the test set. So now when you do the measurement, there is a challenge that you're going to run into. Try to avoid the situation. That's why I'm highlighting that. Try to not measure the two resistances on the same side. And why do I say that? Because now when you did this thing, the current flew from H1 to 0, H0 point, and back to H3, back to the test set. There was no current flow in the H0 bushing. And because there was no flow of the current in the H0 bushing, I never measured the resistance of the conductor that is going through the H0 bushing. And now when I'm going to test the B phase, I'm going to connect to H2 and I'm going to connect to H0. And in that one, I am going to measure the resistance of the H0 bushing, because now the current is flowing through the H0 bushing when you're going to do the B phase, because your connections are from H2 to H0 coming out of H0. So your A and C phase did not take into account the resistance of the H0 bushing conductor, whereas your B phase took that resistance into account. And that could cause mismatch in when you're doing the comparison between the phases. So I will give you some results right here. So the first set of results that you're seeing here, what we did was we did the measurement of B and C phase together, where the current went into X2 and came out of X3. And you notice that they are similar. And I did a single measurement on the A phase. So you notice that A phase is about 150 microohms higher than B and C phase, because B and C phase did not take into account the resistance of the neutral bushing. If I add 150 microohms to the readings of B and C phase, you would notice that all the percentage difference fell within 2%. So again, if you are dealing, and I'm going to repeat that again, if you are dealing with the resistance that's less than 5 milliohms, try to avoid measuring the two resistances on the same side, like high side or low side. Try to avoid that. It is okay to measure the resistance of A phase of high side and A phase of low side together. That's acceptable. But try to avoid measuring the two resistances on the same side of the transformer. This is one other example. As long as your resistance is more than 10 milliohms, that X0 bushing resistance is not going to make a huge difference. You can see that even though I did the per phase and two phase measurement, my readings were not too much different. So this is only applicable when you deal with the resistance that's less than 5 milliohms. Now, some real quick things. Whenever you're dealing with a single phase auto transformer, that's very difficult to test because of the example I gave earlier. It has very high inductance and very small resistance. So L by R, the time constant is very high. It will take you a very long time to get stable measurement. When you have a delta winding on the secondary side, that is also difficult to test. Why? Because majority of the transformers are step-down transformer, meaning that the current requirement on the secondary side is much more, because secondary side of a step-down transformer have higher current, and 1% or 10% of higher current is a higher current, obviously. So you need more current. That's one challenge. And second is that whenever you're dealing with the delta winding, you're dealing with 3 inductances instead of 1 inductance. So keep in mind, big auto transformers that have tertiary winding, those are difficult to test. And whenever you have a delta winding on the secondary side, those are also very difficult to test. And one thing you can do to help yourself is to do dual injection. That would help you in getting results faster and getting accurate measurement. This is an example on a 345 kV single phase auto with a 800 MVA. And you notice that it took us 15 minutes to get a stable reading. That's how long it can take if you have a really large size transformer. So keep those things in mind when you're testing. Try to make use of dual injection. Then once you are done with the testing, make sure that you demagnetize the transformer, because whenever you're going to inject DC current, you're going to magnetize the core of the transformer, and there is going to be some residual flux. And your intention is to leave the core demagnetized. There should not be any residual flux. So how do we do that? We apply the DC current again, but then we flip the polarity. A lot of people used to use a battery to do this thing in the past, but now majority of the test set have this inbuilt into it. You apply the same DC current, change the polarity, and slowly reduce the magnitude of it. You notice that it goes from 100% to 20% to 4% to 1%. And the intent is that you want to reduce the level of magnetization and flip the polarity, so that way you can demagnetize the transformer. This slide would give you a good idea. So this is the hysteresis curve that I talked about. When you ran the test at 10 amps, that's where you were as far as the flux or the saturation is concerned. Now my goal is to bring the flux from this point to this point. How do I do that? So right now the core is magnetized in one direction at 10 amps. So I'm going to apply negative 10 amps to be right here. You see negative 10 amps, I'm going to apply here. So I'm trying to magnetize the core in the opposite direction. Then I go to the step 2, which is applying 6 amps in the positive direction. Now I'm here and I'm trying to magnetize here. Then I go to negative 3.5 amps. I'm somewhere here and I'm trying to bring the flux here. So you see that slowly I'm shrinking the hysteresis curve, and then I go to the lower levels of current, and now I'm working somewhere here. And again, the goal is to reduce the flux back to close to 0 as much as possible. So what you're trying to do is that you start with the level of the test current that you applied, then flip the polarity with the decreasing magnitude to bring the hysteresis curve close to 0. Okay, I'm almost about time, so I'm going to be real quick and we'll try to finish in the next 10 minutes. There is one other method which we can use, which is adaptive Dmag, where instead of using fixed values of the current, what it does is it looks at the voltage times second, which is the flux, and once it measures the integral of the voltage and time, it creates its own customized level of reduction in steps, so that way you can do the Dmag faster based upon the level of magnetization. So you notice that it would quickly go from this point to this point based upon the amount of magnetization that the transformer has. So it's kind of more adaptive based upon which transformer you're testing. And this is some example which shows you that that when you do the adaptive Dmag, you can demag the transformer much quicker compared to the standard practice of a DC current with changing polarity. So this transformer took 2 minutes with the regular method, and with the adaptive method, it only took 15 seconds. When you talk about transformers, you can have a de-energized tap changer on the secondary side and on-load tap changer on the primary side. It is recommended to test all the taps when you are doing the commissioning test, but if you're doing the maintenance test, don't change the tap of a de-energized tap changer. Only test the in-service tap. And the way you want to do the test is that you want to do the test in this order. So you stay at the tap where you are, you test A phase, then B phase, then C phase. The reason for that is that you want to first obviously magnetize the A phase, do the measurement, move to B phase and C phase. And if you're doing commissioning test, then you move to tap number 2 and again go sequentially in horizontal direction. Again, I'm going to repeat that again. When you're testing de-energized tap changer, go in the row format in the horizontal direction. Okay, and when you're testing on-load tap changer, it is recommended to go in the vertical direction. What I mean by that is that you're going to stay on the A phase and test all the taps from 16 rays to 16L. I will start with 16 rays. I've already magnetized the A phase winding, so it's much easier for me to get the reading for 15R, 14R, and so on and so forth. So for when testing the OLTC, you want to go vertically down, meaning that you want to test in a column format. And when you are testing the de-energized tap changer, you want to go in the row format. In the on-load tap changer, you go in the direction from 16 rays to 16L. You are already at 16L. Then for B phase, you're going to go from 16L to 16R. And for C phase, you're going to go again in the downward direction from 16R to 16L. That's the most efficient way of testing. The other thing that's there is that whenever you do the winding resistance, you also check for the make before break operation for the OLTC. On-load tap changer should always make contact with the next tap before it disconnects from the previous tap. So we can check that make before break operation of the OLTC by monitoring the dip in the current. And if the dip in the current stays for more than 5 milliseconds, then we call it as a break before make. So again, you can check the make before break operation of the LTC with the winding resistance test set. The other thing that people do is that they represent the 33 taps on a graph, so that it's much more visible what's going on. Like this first one is the results from a preventive auto tap changer. The bottom one is the one with the reversing switch and selector switch, where you get a nice V-shaped curve, and this one is also V-shaped but with zigzag. The nice thing when you plot all the taps in one place is that if there is any tap that has any problem, it would stand out. So that's the advantage of plotting it on the graph. I'm going to be real fast because I'm already over the time. I'm going to take maybe 5 more minutes and then we're going to wrap up. This is one example where I showed you that if you use a single phase source, you notice that the current is flowing through X1 bushing, goes through the winding, and then it comes back through the XO bushing. So the current is flowing through the exo bushing. Excuse me. But if I were to test two windings at the same time on the same side, you notice that the current would flow from X2, go through the X2 winding, but it never comes out of the XO bushing. It comes out back out of X3. So you miss the resistance of the XO bushing when you do the dual injection of two windings on the same side. So try to avoid that. There are some test sets out there that provide three-phase source. The advantage of using three-phase source is that you can magnetize with three currents at the same time. But there are a lot of disadvantages as well. You notice that you can only use a three-phase source for a Y configuration. You cannot use three-phase source for a delta configuration, because then all the readings would be very error prone, because the currents would flow all over the place. But even in the Y configuration, you notice that you have three currents flowing, but now through the exo bushing, the current is 3 times of those three currents, and that would cause error in the measurement. You cannot do dual injection with this kind of three-phase source, so that's the other challenge. When if you use three-phase source, you would get higher readings because it doesn't take into account the 3 times the current. So keep those things in mind if you are to use a three-phase source. We typically don't recommend that because, again, you can get some erroneous readings. Plus, you can only use it on Y configuration. Delta cannot be tested. You cannot do make before break operation, and you cannot do dual injection. Okay, in summary, real quick. So whenever you do the winding resistance test, two things that are very important is stabilization of the current and the saturation of the core. You need to have enough compliance voltage and enough test voltage to be able to saturate the core. Remember, make sure that you keep the direction of flux in the same direction. Anytime you run into a circuit that is a very high time constant, you would run into a challenge where it would take longer time to get stable readings. And winding configuration is important. Anytime you have a delta winding on the secondary side, it will take longer time. Some other things, per phase testing is recommended, and if you can do dual injection, that's even better. But per phase is the most simple way of doing the testing. And if you were to do the 2 phases on the same side or 3-phase testing, it comes with its own limitations. Whenever you're testing OLTC, make sure that you go vertically down. You stay on A phase, test from 16 raised to 16L, then go in the upward direction for B phase and downward direction for C phase. Your winding resistance is a temperature dependent test. You should always compare temperature corrected readings. All should be referenced back to a common temperature so that you can compare apples to apples. There are some recommendations from industry, 2% between the phases and 5% from the factory test results. Those should be your guideline. Then safety is very important. You want to make sure that you dissipate the energy in the inductor before you take the leads off. And the last point is that you should demagnetize the transformer so that way there is no residual flux. If there is some residual flux, it can affect excitation current or the SFRA test, and your transformer might trip out because of high inrush current if you were to put it back in service with a high level of residual flux. Real quick, I'm going to take 1 more minute to talk about what Megger instruments we have to offer as it relates to the winding resistance. So the first one that we have is MTO 250. It's a single phase current source with 2 voltmeters. It can provide you up to 50 amps. You can control it with computer. It has the Dmag feature, and you can perform the test on all the taps of the OLTC. The other one that we have is the MTO 300. It's our three-phase unit. It tests one phase at a time with all the leads connected at the same time, and you can use the same lead set to perform the TTR test. You just unhook the winding resistance, connect your turns ratio test set, and with the same set of connections, you can run the turns ratio as well. It is PowerDB compatible for the software. It has a 12-inch display that you can use to perform with the onboard computer, can do the Dmag, and you can test all the OLTC tap as well. Then we have our a combo unit, which can do turns ratio and winding resistance together in one box. It's very efficient, one single form where all the results from turns ratio and winding resistance populate in one single form. It's much easier to operate, the same nameplate information. You make your connection one time and do the winding resistance and turns ratio with the same set of connection. And the last instrument that we have is our multifunctional tracks instrument that can do turns ratio, winding resistance, power factor, excitation current, leakage reactance, circuit breaker testing, contact resistance. It can do all of those tests in one single box. The nice thing is that then you are dealing with only one software, so it's much easier to use and operate. Learning curve is small, and you get all your results at one place. So that's our multifunctional all-in-one instrument that can do all of your transformer testing. I believe with this, we are to the end of the webinar. Thanks for listening, and I will hand it over back to Michael.
Thanks, Dinesh. So we've finished up our presentation portion of our webinar, and we'll be jumping into our Q&A session here in a moment. A few housekeeping things. For those of you that are leaving and don't want to stay around for the Q&A, please feel free to fill out our survey over here, and I'll highlight that for you right there. We would really appreciate getting a little bit of feedback, especially growing into our new system here. We love hearing how you guys enjoyed the system or didn't enjoy it. We can always improve. But we would love having any of your feedback sent in over there. We'll also be sending out a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar in about 2 business days. In fact, the link used to join into the session will bring you to a recording of the webinar in about an hour after we wrap up here. So next up, I will want to remind you that on your screen there, we have a little button there to register for our webinar on March 23rd for ground fault location in PV systems. That will be presented by Brian Hammerschmidt. So let's jump into our questions. Our first one I have, I'm going to be directing over to our panelist, Dr. Charles Nybeck. Charles, what could we do when we have a deviation between phases above 5%? And how can we be sure of the type of defect? Oh, I think we might still have you on mute there, Charles.
While Charles, I guess, if figure out, I guess I can respond to that question. Okay, so if in case your readings are more than 5%, I would start off with making sure that I am comparing apples to apples. Those are temperature correction readings. The second thing that I would do is that I would re-perform the test, because I always blame the user before I start pointing towards a transformer. So let's say the readings are temperature corrected. I ran the test again. My readings are still above 5%. If that is the case, I want to validate that with another electrical test. And one way to do that is that if your winding resistance shows higher the deviation, I would start with the excitation current test and make sure that my excitation current are kind of trending in the same direction with the historical measurement. The other thing I would do is that I would perform the SFRA measurement, because if there is something wrong with the winding, I would be able to figure that out in the range, in the frequency range from 20 kilohertz to 400 kilohertz. So I would perform these two tests to see what's going on. The other third test that I would look into is our leakage reactance test that gives me the idea about the core and winding kind of thing. So those were the three tests that I would look into if my winding resistance is above 5% between the phases. And again, I would first blame the user before I start blaming the transformer.
All right. Do we want to quick mic check with Charles? Make sure we got you back.
Yeah, sorry about that.
No worries.
All good now?
Excellent.
Great.
With that, we'll jump into our next question. I'll send that over to Damien. Damien, what is the best current to use to test winding resistance from 10 amps to 50 amps? And what about the tap changer rating and using 50 amps?
Okay, so I thought Dinesh covered this very well. I will say briefly that you don't want to just blindly choose any current. What you want to do is look at what the nameplate rating is of the particular transformer. And with regards to the tap changer is going to need to be, at worst case, the same rating as the transformer. If you think about it from a logical standpoint, if a winding is rated for 1,000 amps and my tap changer is rated for 50 amps, I'm going to have a serious problem. So that kind of addresses the second part of the question. But the first part, look at the rating of the winding, and then, as Dinesh mentioned, you want to stay within 1 to 15%. And I will also add that many common instruments, once you input the nameplate information, they will give you a recommended test current, which is usually going to be somewhere around 1 to 10% of the rated current.
Thanks, Damien. Over to Charles. Is there a level of combustible gases that DC winding resistance testing should not be tested at?
So good question. So obviously, performing DGA testing is very important to determine how, the level of combustible gases that you have in your transformer. And if that exceeds a certain threshold, then obviously that needs to be addressed. But in terms of a winding resistance test, those gases would not necessarily affect that test, or would not cause any issues at that point, because you're injecting current on the windings. So you really shouldn't have any danger in that sense. But obviously, we want to be aware of those combustible gases that are present within our transformer. So that way we can take corrective actions, and if that's the case.
Thanks. Over to Damien. How much of a difference in measurement do you have with a loose connection or carbon contamination?
It's a very interesting question, and actually it's one that's hard to give a direct answer. I mean, there's a couple of things that play into that. How much carbonization are we talking? Are we talking about the beginning stages, or is it severe? As well as with a loose connection. Are we talking about a loose connection that, say, for example, some sort of stranded conductor and it's only, one piece of that conductor connected? Or are we talking about, how severe something's torqued? There's a lot of different elements that go into being able to quantify that. The other thing that complicates it a little bit too is how much current you're using. So for example, if it's a loose connection and I'm only using, say, 1 amp versus 50 amps, the 50 amps is gonna show up a lot more because it's gonna heat that connection up. So unfortunately, that's a tough one to answer, but you will see a difference in the reading if you have those loose connection or carbonation, and it's going to depend on the severity of the situation.
All right. Back over to Charles. What is the internal effect of having an internal resistance difference greater than 2% already from the factory?
So Dinesh covered this, and there's kind of two aspects of this. And one is if the test done in the factory already exceeds that resistance difference of 2%, then that would be cause of some concern in the sense that you would want to have a discussion with the factory, determine what that, the exact, issue there, maybe have it examined further. Now, as Dinesh did mention in his presentation, you can compare your winding resistance measurements to the factory measurements once you receive it, and that can be within that 5% range. But if it's already being tested at the factory before it's being delivered, and those winding differences exceed that 2%, then that may be something that would want to be discussed with the factory to determine why that may be.
All right, over to Dinesh. Is it best to select the current level or auto ranging?
That's a very interesting question, and I'm glad that someone asked that question. I believe it was Gary who asked it. That's a good question, Gary. So think about this thing. So I talked about this thing that you want to be in the range of 1 to 10%. If the test set allows, I would go as high as up to 10%. So let's say I have a test set that can give me 50 amps of test current, and my rated current is, let's say, 200 amp of that winding. So 10% of that is 20. So I want to start by 20. So I will pick a certain level of current if the test set can provide that. So that's your first part, to select the current level. Now, the nice thing that works is that, let's say you said, I want to inject 20 amps, but the transformer has very high resistance for whatever reason. So what the test instrument does is that even though you asked for 20 amps, it would try to strive for 20 amps, but it may happen that because of the high resistance, it might settle at 15 amps only. So it is doing auto ranging after you've selected a current level. So always start with 10% if you can, and then once you select that current, the test instrument would try to obviously get to that level, but it would auto range based upon whether it can do that or not.
Thanks, Dinesh. Over to Damien. We use a low resistance ohm meter for winding resistance test measurements. It takes a lot of time to stabilize. Which test instrument is better?
So this is a question. In my tenure with Megger, I have received this question less and less as the market becomes more educated that a traditional winding resistance test set is the better way to go. As Dinesh pointed out, a lot of the phenomena as far as like a low resistance ohm meter can have the current to push, but the problem, one of the problems is going to be the voltage it outputs. I looked up the specifications on one of the units, one of the popular units we sell, and the compliance voltage, or the voltage it's able to push to their output, is 20 millivolts. And we've talked about 50 volts as an example of some of our winding resistance test sets. So that should help to answer that question of why it's taken so long. You're not able to overcome that inductive the inductance of the winding in order to get that stable reading. So that answers that portion. Now there's a couple other important parts too of why a low resistance ohm meter should not be used, and that is the discharge circuit. Once you have charged up that winding, you need something to properly discharge it, and low resistance ohm meters do not have that. And then lastly is the Dmag capability. Once you have finished all of your winding resistance testing, you need to demag the transformer, and low resistance ohm meters do not have that functionality. So the long story short is that's not the right instrument to be using. You need to use a dedicated winding resistance test set.
Thanks, Damien. Throwing this next question over to Dinesh, what do you mean by exceeding the saturation knee? I think this question came up early in the presentation. Oh, and I think we might have you on mute again there, Dinesh.
Sorry about that. So I will try to explain that a little bit. I can kind of more in depth. So the way we define the knee point is the point beyond which the relation between voltage and current is not linear. That's the kind of definition for the knee point. And if the flux in the core is beyond that point, then we say that the core is saturated. So when you perform the winding resistance, the goal is that I want to overcome the inductance of the circuit. I shared one circuit, which is the equivalent circuit of a transformer, and it had a leakage reactance component X1 and X2. So what happens is that once you apply enough voltage for enough amount of time, you develop enough flux that now the material that we are talking about, the core, the domains are aligned, and what it does is that it reduces the effect of inductance, which is the resistance to the flow of the current. It neutralizes that, and once you have neutralized the effect of inductance, then it is much easier for you to push the current and stabilize the current. And once you have stabilized the current, that's when the L di by dt goes away. And if I don't have the L di over dt, which is the rate of change of current, then it is obviously now easy for me to do V over I. So I want to set up enough flux which would take it to the saturation, and then I can get rid of L di by dt and get my resistance measurement.
All right. Next question is to Damien. What is the purpose of correcting to a reference temperature?
It's a good question. And one thing to remember about remember about resistance is that it's temperature dependent. So whether we're talking contact resistance or winding resistance, or we're talking insulation resistance, it doesn't matter. Resistance is going to be temperature dependent in an object. Now, when we talk about conductors, which is what we're talking about with the transformer winding, the higher the temperature, the higher the resistance. The lower the temperature, the lower the resistance. So one thing we can't control in a factory, you can pretty much control the temperature of the winding. So I could theoretically not have to worry about adjusting it to a certain temperature. But when I'm out in the field, I have no control over the asset temperature when I'm there. So the idea of temperature correction or doing a reference temperature is that no matter what temperature I take the measurements at, I have a reference to go back to for comparison purposes.
Thanks, Damien. I know we're sprinting up to our deadline here, so we're going to have time for one more question. I'm going to throw that over to Charles. Charles, which transformer current should be used as a reference, either base or force cooled?
So this is a good piggyback off of what Damien just mentioned. So as he mentioned, resistance is temperature dependent. So ideally, when you're performing this test, not ideally, when you're performing a winding resistance test, that transformer will have been taken offline and isolated. And what typically happens is that sets and comes to an ambient temperature at that point. So there will be no forced cooling going on. So we would want to utilize that base as a reference for our current measurement or for our current application. So it kind of goes along with exactly what Damien said in the sense that, it's temperature dependent, so we really want that to set at an ambient temperature and then perform the measurement, which we would reference the base.
Thanks, Charles. So it looks like that's all the time we have for our Q&A today. I know we have a lot of questions we couldn't answer online, and I'm not exaggerating when we have close to 80 from our audience here. We have a lot of really inquisitive minds on here. So we'll try and reach out to as many of you as possible offline to answer your questions. If you'd like to improve your visibility on those questions, please feel free to contact us there in the box on the top right, or drop an email to broadcast@megger.com, and we'll try and reach out to you in a timely manner. But with that, I'd like to thank you all for attending. If you could, please remember to answer our survey. We'd love to know how you like this new space, how we can improve going forward, what you like, what you didn't like. Because we want to give you the best experience here when learning such impressive topics. But once again, I'd like to thank you all for joining in. I hope you enjoyed our session here today. Thank you to our presenter and our panelists here. I know I had a great time today, and I hope you all did too. But furthermore, I'd love to have everyone here have a phenomenal weekend, and I wish to see you all throughout the year as we continue our webinar series here. But with that, I'm going to wrap things up. It's going to prompt up a survey, but have a good one, guys.
Thanks, everybody.